mention topology? No. No. Wondering.
What is topology?
I'm sorry?
What is topology?
Oh, you've been doing topology, you just didn't know it.
Oh.
Topological spaces, well, metric spaces are particular examples. And basically it's spaces where you have a concept of open sets, closed sets, and so on, that satisfy certain axioms. So it's a bit more general than metric spaces. I wasn't sure whether you were planning to do any of that or not. Okay, so last time we proved following inequality. Let me just write it up again. And this was lemma 4.4. And it said if an is in little l p and bn is in little l q, where 1 over p plus 1 over q is equal to 1, then sigma an bn in absolute value is bounded by the p norm of the ans times the q norm of the bns. And remember, although I'm using the word norm, we have not yet proved that this is a norm. So that is the next result. This is theorem 4.5. For p between 1 and infinity, sigma absolute value an to the p to the 1 over p is a norm on little l. Now, as I mentioned before, we've already done the case p equals 2, and we got this fairly easily out of the Cauchy-Schwarz inequality that holds in that situation. However, for other p's, it's not quite so simple, so we're going to go at it a little bit indirectly. I'm going to introduce something else, and the something else will be easy to see it's a norm, and then we'll prove that something else is actually equal to the p norm. So for sequence an in little lp, here is the something else. Let us define capital Phi of the sequence an to be equal to the supremum of sigma an bn, where the supremum is taken over all sequences such that q norm of the bn's is equal to 1.
Is there a reason you have 2 brackets for the A and BN?
It's a sigma.
It's a sigma. Okay. That makes more sense.
Oh. Yes, this is a sum. N equals 1 to infinity. Secondly, phi of an is less than or equal to p norm. And thirdly, p norm is less than or equal to phi of an. If we can do those three things, then that will prove the result, because 2 and 3 say that this phi is just the p norm in a disguised form, and 1 will then tell us that we actually do have a norm. Okay, so the first thing, why is it a norm? Well, it's going to be non-negative. So if an is in little lp, let ak be the first non-zero term. I'm just excluding the zero vector because it's quite evident that phi of that is 0. And then define bn to be equal to 1 when n is equal, plus or minus 1 when n is equal to k, and 0 when n is not k. Then sigma an bn, depending on whether we took plus or minus here, is plus or minus ak. So one of those is positive. And the Q norm of this sequence, just plug it into the formula, and you find that it's 1. And therefore, since phi of the sequence an is the supremum of all numbers we can get in that way, we find that phi of an is strictly positive. Now, we don't want the supremum to be infinite. So if we apply lemma 4.4, we get that phi of any sequence an is bounded above by the p norm of the ans times the q norm of the bn's, but that's always 1. Since we are using sequences bn with the q norm equal to 1. And incidentally, we have also proved number 2. Now, just from the nature of the definition, if C is a constant, then phi of the sequence CAN equals absolute value of C, phi of the sequence AN, is immediate from the definition. The constant is just going to factor out. So the main thing is the triangle inequality. So if AN and AN hat are in little LP, then phi of the sum this is the supremum of the sum from 1 to infinity, AN plus AN hat times BN, such that sigma absolute value BN to the Q is equal to 1. But the supremum of a sum is less than or equal to the sum of the suprema. So this is less than or equal to the sup of sigma AN BN plus the sup of sigma AN hat BN subject to absolute value Bn to the Q equals 1. So that's the triangle inequality. And therefore, phi of AN is a norm on little LP. Well, as I pointed out, we've already proved number 2, so the last thing we have to do is prove number 3. So number 3 says that sigma absolute value AN to the P to the 1 over P is less than or equal to phi of the sequence AN. Now both sides are homogeneous for scaling. So it is enough to show this when sigma AN to the P to the 1 over P is equal to 1. suitable choice of the bn's, we'll get one of the terms in the soup to be at least 1. And the way I do that is you can always modify a sequence to put it in one of the other spaces as follows. So let us consider the following sequence. It's going to be absolute value of an raised to the p over q power if an is greater than or equal to 0, and it's going to be negative absolute value of an the p over q if an is negative. Then the absolute value of bn, the minus sign goes away, so in all or both cases, this is absolute value of an to the p over q. So when I raise both sides to the q power, I get absolute value of an to the p. And when I sum, I get this. Now, because it came out to be 1, I can take the qth root, and I find that the q norm of the bn's is equal to 1. So this is a useful trick for converting a sequence in one LP space into a sequence that's in another one. I can just scale in the powers here to make it summable in some other space. Okay, so that is a viable choice for the sequence that appears in the supremum. So phi of an is at least what you get when you plug in any term, so sigma an bn. And now what is sigma an bn? Because of the minus signs, when the an's are negative, product of these two numbers is always positive, and it's equal to the sum of the absolute value of an, and the power is 1 plus p over q. Now, since 1 over p plus 1 over q is equal to 1, if I multiply through by p, we get 1 plus p over q is equal to p. And so the exponent here is actually p, and therefore p of the an's is at least sigma absolute value an raised to the pth power, and that is equal to 1. So that's what we needed to show. Therefore, P of an is at least the P norm of the sequence. So now we have inequality both directions, and therefore equality. And since P was a norm, this now proves that the P norm really is a norm. One gets a little nervous arguing this. If you take notation that's too suggestive, then it's easy to slip in things that are perhaps not quite true. But if you look through the proof, you'll see that at no point did we ever do anything that involved this being a norm. So at this point, we do have a proof. Really is a norm on the globe. So, as you can see, it's quite complicated to show that that is a norm. This is about the easiest proof I know. So there isn't some trivial way of doing it, I don't think. Okay, so just like little L2 and little L1, these spaces are complete. So this is going to be complete as a metric space. So proof let's consider a Cauchy sequence capital Xn in little LP. So we have to find a candidate for what it might converge to, and then show that it really does converge to it in the P norm. So let us write capital Xn is the sequence x sub n1, x sub n2, x sub n3, and so on. So, given epsilon greater than 0, we can choose capital N so that capital Xn minus capital Xm in the P norm is less than epsilon for all m and n greater than or equal to capital N. on in terms of the sequences, what this says is that the sum r equals 1 to infinity, absolute value of x nr minus x mr raised to the pth power. Now, to get the norm, we would have to do a 1 over p, but I'm going to raise everything to the pth power for convenience. So this will be less than epsilon to the p for all m and n greater than or equal to capital N. So for any fixed r, this of course is a sum of non-negative terms, and so any one of them is going to be less than epsilon to the p. So absolute value xnr minus xmr is going to be less than epsilon as long as m and n are large enough. Of course, that means that that sequence is now Cauchy in R. So by completeness of R, we can define x sub r to be equal to the limit as n goes to infinity of x sub nr. So the sequence formed in this way, well, we have several things to do, but this is going to be the candidate for our limit. So we have to show that this sequence is in little lp, and then that the original Cauchy sequence converges to it. So define capital X to be the sequence little x1, little x2, little x3, and so on. So we show that capital X is in little lp, and that the difference, capital X minus xn, in p norm goes to 0 as n goes to infinity. So let me name this. Let's call this inequality star. So before I erase it, from star, we have the following. Well, if the sum from 1 to infinity is less than epsilon over p, then the sum from 1 to any finite stage is also less than epsilon over p. So we have that the sum from 1 to capital R, absolute value xnr minus xmr to the p is less than epsilon to the p, and this is for m and n greater than or equal to capital N, and that's not a problem if I'm doing it on a finite number of terms. So let m go to infinity. That's permissible because that inequality is true for all m and n greater than or equal to capital M. And what we get is that the sum from 1 to capital R, absolute value xn r minus x sub r raised to the pth power. Now the less than may turn into a less than or equal to in the limit. Less than or equal to epsilon to the p. Well, we've lost m. So this is for little n greater than or equal to capital N and any value of r greater than or equal to 1. That being so, I can fix n and let capital R go to infinity. So letting capital R go to infinity, what we get is that the sum from 1 to infinity absolute value xnr minus xr raised to the pth power is less than or equal to epsilon to the p, and this is going to be true for any n greater than or equal to capital N. So here's a value for which it's true. Take little n to be capital N. Then what this inequality says, the sequence that consists of x capital N sub r minus x sub r equals 1 to infinity, is in little LP. Since the sequence consisting of the x sub r's is the sequence coming from capital N minus the sequence coming from this difference, the first of these is in little LP, the second one we've just shown is in little LP, so their difference is in little LP. And we'll also be using this equation again, so let me call this one double star. So since this is true, we get that the sequence capital X equals little xr is also in little LP. that's what we needed, and so little LP is complete. For P between 1 and 2. We already know little L1 is, and we already knew that little L2 was. So that gives the full set. So that's basically what I wanted to do. But let me just make a remark. Now, when you get into 447, you'll learn about general measures and integrals with respect to measures, but you don't need to be that sophisticated. We could define capital LP of 0, 1 to be the set of functions f such that the integral 0 to 1 absolute value f of x to the p dx is a finite number. So this would be the analog of the little LP spaces, which basically are discrete, they're defined on the integers. Here we look at functions defined on an interval, and we use something like this. So for 1 less than or equal to p less than infinity, the quantity integral 0 to 1 absolute value f of x to the p dx, and then raised to the 1 over p, this quantity defines a norm It's completely analogous to what we've just been doing. It defines a norm denoted by the p naught. So you can translate all of this from sequences to functions, and there's nothing special about the interval 0 to 1. It could be any interval here, or even 0 to infinity, functions that are integrable over infinite intervals. And all the results go through in an analogous way. And so these spaces are also complete. However, if you think back to the proof that we just did, what we had to do in order to take limits in that infinite sum was we had to drop down to a finite sum, take our limit, and then go back to the infinite sum. So there was a little bit of trickery involved in getting things to work. It's the same situation here. The proofs require some theorems interchanging integration and limits. So the sticking point that we would encounter if we were to do this now is the following. We would encounter this problem. Limit n goes to infinity, integral 0 to 1, absolute value fn of x minus f of x to the pth power is that equal to the integral from 0 to 1, the limit as n goes to infinity, absolute value fn of x minus f of x power dx. That would be the problem that we would have to deal with. And it all works out, but it's not obvious. So you need a theorem that will do such things for you. So this needs a theorem. So there are quite general theorems that deal with limiting processes in the presence of integrals. We just haven't learned them yet. So that is what is required to extend all of this to the setting of what's called big LP, colloquially, deals with functions. Okay, so we will not meet on Wednesday. So have a good Thanksgiving. And we will meet the following Monday. Now, you may not have noticed yet, but I've put a set of practice problems on the web. So I'm thinking we should start discussing those on the Monday after Thanksgiving. So try to have a look at them before that. That will allow more time on Wednesday if there are other questions. So let us do that. So I think at this